All right, you guys did well on 2.1, so I don't want to spend a whole lot of time going over that stuff. But what that kind of gets you geared for, it's called inductive reasoning. Basically, you recognize patterns, right? See a pattern, kind of replicate that pattern, and project, kind of have a mind frame of what the next couple terms or next couple things are going to look like inside that pattern. Now, we're just projecting. So if I say 2, 4, 6, you're going to project that the next ones are 8, 10, 12, right? But they don't necessarily have to be that. We're just getting our best guess. Does that make sense? Okay. What this chapter is about, and what parts of the next couple chapters are about, is how we phrase our math so that we so we can start proving things to be true. We start classifying things accurately. In the event that I never create one rule in mathematics that violates another rule, okay? Regardless of what branch of mathematics that we're in. So if I create a phrase in Algebra 1, okay, in a rule in Algebra 1, that should never violate something in geometry, or never violate something in calculus. Does that make sense? And something that we create, some theorem that we come up with in calculus, never violates a rule that we created earlier. Okay? Because if we do that, then we've got an issue inside our system. Is that all right with everybody? Okay. So we're kind of walking our way through how a lot of things in math are written, are theorems. We've seen some postulates already written this way. We're going to talk about kind of the format that they're written in. And then we end up with things that are called corollaries and lemmas, which really aren't things that we really need to concern ourselves with right now. And we really haven't talked about theorems yet, but they're just basic rules that we can prove to be true. Okay? Postulates were rules that we couldn't prove, right? I can show you a picture. We had to justify it that way, convince ourselves that way. But we had to take those rules for what they were without any formal proof. Theorems, corollaries, and lemmas, we can prove those things. We can show why they may or may not be true. And this concept of conditional statements is the foundation of being able to do that. And to be able to read something and fully understand what they are saying and what they are not saying. Okay? Gage, can you drive yet?
Yeah.
Okay. So you go home tonight and you say, Mom, can I have the car keys? And she says, if you clean your room, then you can have the car keys. Okay? She just gave you a conditional statement. She just told you, if you meet my conditions, you can have what you want. Right? We hear those from our parents all the time, right? Okay? Mathematically speaking, everything we talk about for the most part is going to be presented to us in thinking. If this occurs, if this is true, okay, then this can happen. Okay? For instance, if x equals 2, then 3x equals 6. Would you agree with that phrase? Okay? That's a conditional statement. You've dealt with that a lot through your previous years, right? Okay? But if this is true, then that is true. If I meet this concept here, then that's true as well. Okay? So those are conditional statements. We're really worried about what they say and what they don't say, and then how we interpret their meanings. So a couple things here, just some generic elementary style questions. If it is like team, then practice will be canceled. So the only way you practice right now, if that's the phrase I have, the only way it's canceled is if I meet the requirement that it's like team, right? If it's 320, then school's over. The only way that I'm going to meet this requirement right now is if this 320 is met. And so forth with that daughter. Okay? So those are just generic if-then statements. Pretty much all of our phrases that we use and the way we conduct ourselves and think inside normal everyday life is a collection of a lot of if-then statements. Okay? If the bell rings, what are you going to do? You're going to leave class. So if the bell rings, then you leave. Okay? If it's mid-period, then the bell rings, then you go to lunch, right? Okay. So you've got the way you progress yourself through your life is a bunch of if-then statements. Okay? And that's the way we think about a lot of things, but now we're going to kind of try to slow things down, the way we think about them, put them on paper as if-then statements and try to interpret exactly what they're saying and try not to overanalyze things. Because that happens, gets us in trouble quite a bit when we do that. Here it says, if two lines intersect, then they do so at a point. That's a math if-then statement that we use in the past, right? Okay. If you can think about two lines intersecting, so you have to have that piece of information. Do these two lines intersect? Okay. Then they do it at one point. Would you agree with that? Okay. Do those two lines intersect? No. Okay. So I'm not even worried about that phrase anymore, right? Because I didn't meet the if part. Okay. I don't have two lines intersecting, so there's no reason for me to look at the then part and understand the then part. It's better if two planes intersect, then they do so at a line. So these are some postulates that we've talked about in the past, and we can rephrase it as if-then statements. If we can recognize that we've met that criteria, and I always think the if part is kind of a picture that they provide you. You can visualize that picture in your head. Okay, what is the conclusion? What is that picture going to provide you? If I can picture two planes intersecting in my mind, then I see the development of that line when they intersect. Anybody interested in like computer programming, software, video games, that kind of stuff? Okay. Everything you do on your computer is an if-then statement. Okay. If I hit Alt Control Delete, what's the computer do? Yeah, it goes to the taskbar thing, right? If I hit Alt F4, my computer just closes everything out, right? Okay. If I hit the escape key, it does something different, right? If I hit my control arrow, it turns my screen, right? So in the background, the computer is programmed as if user pushes these keys, then computer do this function. Okay? And the computer only does that function then when those keys are pushed. So if I hit Alt Control Delete and that taskbar shows up, okay, I will never hit Alt Control Delete and something else happen, right? Or that taskbar will never come up if I hit Alt Control R. Okay? It only comes up if I do what has been defined in the if part. Does that make sense, everybody? Okay? Down to like it's very like primitive state is binary, right? Zeros and ones, you know about that? That's how a lot of all computers are programmed using binary, but there's writing tools like JavaScript, HTML, and that kind of stuff that kind of makes it more user-friendly and easier to do. But basically, zeros and ones are a bunch of true and false statements. Okay, saying if I have 3 zeros, a 1, a 0, then computer do this. And those zeros and ones represent switches for on and off and stuff like that. But it's all about if this is done, then what is the conclusion? What should the computer do? What should the calculator do? Whatever technology you're using. So this stuff is very important in a lot of the things that we do. Those of you that are big-time gamers, okay, your gaming cannot be conducted without an understanding of if-then statement. Okay. So if you guys have played like games and you get like a glitch, right? Okay. And you do something that's not like physically expected inside that game. It's because somewhere in the logic of that game, there's been a typo or something in the if-then statements. Okay. And that allows you basically to get into a loop that wasn't intended to be created. Okay. And that's why games come out with patches. That's why iOS got with all these updates on it and stuff. Because the coding, if they correctly written at some point, and there's a typo or something that needs to fix something. Okay. And we do that with a lot of if-then statements. Okay. Here's the concept. Here's some definitions that we need to realize. The conditional statement. If Gage cleans his bedroom, then he gets the car keys. His mom gave him the condition to meet of cleaning his bedroom. All right, so that's what we call these conditional statements. You have to meet some requirement first for the then part to occur. Okay, so it's called just a conditional statement by definition, very general, basic, boring definition, because just call it an if-then statement. Okay? So any phrase that you see that has an if-then kind of philosophy is a conditional statement. The hypothesis is the phrase that comes after the word if and comes before the word then. Okay? So for if Gage cleans his bedroom, then he can have car keys. Cleans his bedroom is the hypothesis. Okay? Just a phrasing, a word that we want to be able to categorize these if statements. Okay? The conclusion is then the result. It's the then part. It's what he gains from cleaning his bedroom, right? What happens is that you can think about all the different types of if-then statements we can create. Okay? And right now, when we just create an if-then statement, I don't even care if it's true. Okay? If it's September, then it's snowing outside. Probably not true here, right? Okay? I don't care. It's still an if-then statement, right? Okay? So all the if-then statements that there's an infinite number that you can create, whether they're true or false. The hypothesis part, we want to just condense that down to a generic statement that just takes place of all the infinite number of generic statements you can create. Okay? Or, I guess, real statements you can create. So, Gage cleaning his bedroom, or it being September. If we go back to the examples, I think one was if it is hiking, one was if it's 3:20, one was if you have a daughter. All those phrases, we just categorize them down and we call them P. Okay? All your hypotheses go down to just P. And it's a little bit easier to talk about. Does that make sense? Okay? So I don't have to write out a real long phrase to understand some of the things that we're going to do. All your conclusions, we just classify them as P. Okay? Same reading. So we read every if-then statement should be if P, then Q. If some P, whatever that phrase is, then I get some Q, whatever that phrase is. Another way you're going to see these written is using the word implies. Okay. P implies Q. Okay. If I'm doing something in class where I say, hey, it's Thursday, we haven't had a test or a quiz in 6-7 days. Tomorrow is my favorite day of the week. If I were you and I was preparing for a class that I was teaching, that maybe I'd prepare for something. What am I implying? If I'm doing all this, if I'm saying all these things, then probably wisdom won't, right? So I'm implying there's I'm not coming out saying that there is one, but I'm just implying. And that's what this kind of says. This occurs, it implies that this is going to occur. Okay? If P occurs, then it's implying that Q is going to occur. Early on especially, and you're going to see it sometimes in your math Excel, they're going to flip back and forth between if and then statements. These two things mean the same. So whenever I see this one, I always cross the implies out, replace it with then, and then I put an if out there. And I get back to the original, just more basic if then statement. Okay? If you do that a handful of times, eventually you're going to remember, oh, well, I can read implies just like an if-then statement. I don't need to rewrite it. Does that make sense? Okay. Don't worry about that Venn diagram right now. We'll get to some examples later on that make that Venn diagram make a little bit more sense. Just another slide here to show the hypothesis and conclusion and where they're at. It's going to be very important for us to identify those things. Let's say I say if, go back to Gage again, if Gage cleans his bedroom, then he gets the car keys. And then I have another conditional statement that says if Gage gets the car keys, then he will go to the movies. I can make a conclusion. I can make a new statement that says if Gage cleans his bedroom, then he goes to the movies, right? Because there's a link between those two original if-then statements. Okay? And it's going to be important that we're able to identify the hypotheses of those first initial conditional statements and the conclusions of those two initial conditional statements, so I can develop that new one. And that'll be something to do tomorrow and the next one. If I say if Gage cleans his bedroom, then he gets the car keys, and I have another phrase that says if Gage is 20, then he is married. If I have those two conditional statements, whether they're true or false, is there any linkage between those two that's making a new one? There shouldn't be. Okay? Nothing was related, right? We'll talk about that. So if P, then Q. Okay? If P, then Q. Be able to understand that hypothesis and understand that conclusion and be able to identify them in every statement we come across. Just another slide here talking about how to locate those. So these statements, these if-then statements, a lot of times we want to know, is this if-then statement true? Is this if-then statement false? Okay? And this goes all the way back, go to the computer programming thing. The zeros and ones, they're basically on and off switches. They're basically for false statements. Okay? And the values for like a true would be a 1. I think a value for false would be a 0. On would be 1, off would be 0, whatever. We're interested, okay, in the expressions or the sentences that we see, and just interpreting, is it a true statement, capital T, or is it a false statement, a capital F? And then we move on. Okay? That's called a truth value. Okay? Not necessarily a number you're getting back, right? It's a characteristic that's associated with that statement. Okay? It says in order to show a conditional is true, okay, you have to show that every time a hypothesis is true, okay, and the conclusion is also true. So if I wanted to show that the conditional statement that if Gage cleans his bedroom, then he gets the car keys. If I want to show that that is a true statement through the entire universe, every single day, every single instant, that's going to be a true statement. And I have to be able to show that every time he cleans his bedroom, there's a direct result of him getting the keys every single time. Okay? Do you get the keys every time you clean the bedroom? Oh, you got your own keys. Okay. That's what we want to do. And it's going to make a lot more sense when we see an example here mathematically. But we want to make sure that the only time that I can say a conditional statement is true is if the hypothesis is true and the conclusion is true all the time. Okay? To show that a conditional is false, I want to show that the hypothesis is true, but then show that there's a counterexample that shows the conclusion is false. Okay? And we'll see some examples of that as well here in a moment. Okay? But we're interested in being able to show things true and show things false. In math, it's really, 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 really hard to show things true all the time. So I want to show something true. I have to show it basically true an infinite number of times. If I want to show that two adjacent angles are complementary, okay, I have to show that regardless of the two angles that I come up with, add together they have to equal 90 degrees. So I have to do that for an angle of 1 and 89, an angle of 2 and 88, an angle of 3 and 87. But I also have to do it for an angle like 45.45, 7321 and its complement. And then I got to do it for 1223, 847 and its complement. So there's an infinite number of different groupings that I could use to add to 90 to show two angles of complementary. So there's an infinite number of possibilities there to show something's true. And I have to go through and work through everyone. It's really hard to do, right? To show something is true an infinite number of times, you're going to die doing that, right? Okay? But to show something is false, I just have to show one time where it's false. You've heard the phrase, like one bad egg ruins the entire basket, right? Okay? One bad gauge in a classroom ruins the entire classroom, right? To show something false mathematically, you just have to show one instance of where it's false, and the whole phrase is false all the time. Right? Does that make sense? Okay. It's truth value would be false. When we talk about just some key things here that we're going to do in a moment, we're going to negate things. Okay. Negate, if you think about an English class, when you negate a phrase, and you put the word not in it, okay? Okay. Maybe you're in Spanish and you do negations in Spanish. Did you have that? Yeah? Huh? Negations? You guys do negate stuff, do negations of things. It's just putting the word not. Okay? Just some symbols here. The phrase that you see, or the notation that you see for, like if I say if not P, then not Q. A lot of times we don't like to write the word not because it's, again, we're kind of mathematically lazy in our writing. So we don't like to write that word not, so we substitute it with that tilde out front, and that just means not. You ever see that tilde in not. Okay? So we read that not P. Now here's the thing, if you say that the water is cold, the negation would be the water is not cold, right? Now, have I told you that the water is hot there when I say it's not cold? No, the only thing I've said there is it's not cold, right? It could be lukewarm, it could be room temperature, it could be boiling, I don't know. Okay? I just know it's not cold. Make sense, everybody? And that's where we get ourselves into trouble a lot because of how we deal with things in English. When we get into the math world and we start negating things, we think completely just the 100% opposite, right? I think it's not cold, it's got to be hot. It doesn't necessarily have to be a varying range of not cold. It could be warm, lukewarm, whatever. Okay? It says you use negations to write statements that are related to conditions. Every conditional statement has 3 additional statements that are linked to it. Okay? And we're going to talk about what those are here in this next slide. All right. This is kind of the nuts and bolts of this entire lesson, and what you're going to be asked to do a lot in the homework that you see. They're going to start you with a conditional statement. Okay? Doesn't matter what that conditional statement is. Doesn't matter if that conditional statement is true or false. Okay? They're starting us here with this first initial conditional statement. Okay? Starting with that one, it says if we go all the way to the end of here, it says if P then Q, right? If P then Q. Okay? So we read the actual example. It says if measure of angle A is 15 degrees, then angle A is acute. What we want to do, we want to see if that's true or false. So to show whether that's true or false, we have to think about all the infinite situations that could happen if I have this correct. So think about this. If I give you all an angle at 15 degrees, okay, is it, and that's always true, so picture that 15 degrees in your head, or I give it to you, it's in your hands. If you have that 15 degree angle, is it always acute? Yes, we know what acute means. Acute means less than 90, right? Okay? So, anytime I give you a 15 degree angle, okay? Give you one today, give you one tomorrow, give you 5 today, 5 tomorrow, whatever. Whenever you receive a 15 degree angle, you could always say that it's acute, right? If measure of angle A is 15, then angle A is acute. That is a true statement, a true condition. Hopefully you guys agree with that, right? Okay. And now we do the converse. The converse, okay, this is how to write it. You exchange the hypothesis and the conclusion. If you look over here in our generic terms, it just takes the if P then Q, it takes the P and it writes it after the word then, it takes the Q and writes it after the word if. Okay, so if Q, then P. So now the converse is basically taking the blue stuff and writing that after if, taking the red stuff up here and writing it after the word then. If angle A is acute, then measure angle A is equal to 15. So now I want you to ask, if I give you an acute angle, if that part is true, give everybody an acute angle, is your acute angle 15 degrees? Does it always have to be 15 degrees? No. That's what that phrase is saying. It's saying it has to be 15 degrees. But we know when I give you an acute angle, it could be 30, it could be 20, it could be 10. Okay? So that 30, that 20, that 10, that 45, the 89.99999, whatever the angle may be, is a counterexample that shows this statement false. Oh, that's not enough. Okay, that counterexample being 30 degrees or 40 degrees or whatever. Okay, could it be 15 degrees? Yeah, there's one situation there where that would be true. But there's also a lot of other situations where it's false. It's false. So whenever I can find a counterexample, conditional is false. Okay. The inverse, okay? The inverse says you're going to take the original conditional statement. So you're going to take this phrase up here, and you're going to negate the hypothesis and the conclusion. You're going to put the word not. Okay. Now, be intelligent about where you put the word not in. You want to make sure that's grammatically correct. Okay. And here, mathematically, okay, we're saying if measure of angle A is 15 degrees up here, and down here, this phrase here says is not 15 degrees, right? Okay. So if measure of angle A is not 15 degrees, so I give you all an A. and it's not 15 degrees. Is angle A acute? Or does it have to be acute? So I give you an angle, it's in your hands, keep your eyes closed. Okay? And I tell you, hey, it's not 15 degrees. Can you make the argument then that it is not acute? No. If it's not acute, what's it have to be? Doesn't necessarily have 50, 90, okay? So if I give you an angle that's not 15 degrees, if you were to say this statement is true, if you were to say this statement right here is true, you were saying that the angle that I gave you, if it's not 15 degrees, then you're saying that it cannot be 90. Okay? So I'm just telling you it's not 15, right? It's not 15. It leaves the door open to be 90, 91, 92, could be 80, could be 50, could be an acute angle, right? Okay. But there's counterexamples where it could be 90, it could be 91, it could be 170. Okay? So this is also false. Okay? We have counterexamples. I just tell you you don't have it. You have an angle that you know it's not 15 degrees. You can't classify it as acute. There's so many other things it could be. Does that make sense? Okay. The last one, we call it a contrapositive. Okay, contrapositive, don't necessarily know where a lot of these phrases, these terms come from, where their origins are. But contrapositive says that we're going to negate the hypothesis, negate the conclusion, and then we flip them. Okay? So really, this final one, the contrapositive, is the collection of those two. It's doing those two things simultaneously to the first condition. Okay? The way I like to do it is I just look at the original conditional, I put the words not in both parts, and then I flip it. Okay? So if we do that, put the word not in here, and the measure of angle A is not 15, then the measure of angle A is not acute, and then put the blue after the word if, the red after the word then, you get that phrase right there. Okay? Contrapositive negates both the hypothesis and conclusion, and then you flip it. Okay? A lot of times you're going to hear me say that this is the contrapositive is the converse of the inverse, or the contrapositive is the inverse of the converse. It doesn't matter. Okay? But the inverse of something just means I'm negating it, right? The converse of something just means I'm flipping it. Okay? So if I negate the flipping, so an inverse of the converse, I create a contrapositive. Okay? Wrap your head around that. Make sure you understand these four things. When I look at this, if A is not acute, so I give you an angle, close your eyes. I tell you it's not acute, then what do you know about it? It's 90 or greater, right? Okay, so it's not acute, it's 90 or greater. Then, if that's the case, it can't be 15, can it? Okay? So that statement would be true. Do you agree with that? If I give you an angle, I tell you it's not acute, then that angle is not 15 degrees. Okay? So that would be a true statement. All right? We go through a lot of this stuff. It's going to be, I think, sometimes difficult for us to recognize whether a statement is true or false. I have an issue just wrapping my head around a lot of things in regards to when they put the word not into something. Okay? For instance, the measure of angle A is not 15 and angle A is not acute. I have trouble in my head, the way I'm programmed, I have trouble answering whether that's true or false. Okay? But I know a little bit, and I'm going to teach this to you here in a moment, that's going to allow you to answer that with really not even having to look at that phrase. Okay? Notice up there, if the conditional statement, it was true, right? The contrapositive was also true. Okay? If I don't know how to answer this one, and whether it's true or false, I go up to this one and determine what it was. If that one was true, that one will be true as well. If this one was false, what do you think this one's going to be? False. Okay? The inverse and the converse, they're both false right there, right? Okay? If this one's false, what do you think you know about that one? It's false. Okay? The way I remember this is the two types of conditional statements that have the word verse, inverse and converse. They always get paired together. One of those is true, the other one's true. If one of those is false, the other one's false. Okay? In the conditional statement, in the contrapositive, they always get paired together. Okay? That idea is a fact about math. Okay, get all the way down here to this slide here, and it says, clear this out real quick. When you find two statements that have the same truth value, so both are true or both are false, we said they're logically equivalent. Okay, that's the vocab word. We're just saying two statements are both true or two statements are both false. Conditionals and contrapositive are always logically equivalent. Okay? Converses and inverses are always logically equivalent. Okay? So here's the thing that I kind of tell people. If I get a phrase that, where'd it go? There we go. If I get a phrase get there. There we go. If I get a phrase, don't worry right now. Come on. Don't worry about what I've called these as converses, inverses, contrapositive, or anything like that. If I get this phrase right here, and I struggle answering that, I'm going to say that is a conditional statement. All of those are if-then statements, right? So all of them could be original conditional statements that I'm providing. If I can't answer whether that's true or false, I could create the converse of that, I could create the inverse of that, and ultimately the contrapositive of that, right? If that's my conditional statement, I can't answer whether it's true or false. I want to try to figure out what the contrapositive is. And the contrapositive of that, okay, if angle A is acute, then measure of angle A is 15 degrees. I want to answer that. And we know that's false, right? Make sense? Okay. So the contrapositive of this would be false. So if this is the original conditional, what is it? It's false as well, isn't it? Okay. Conditionals and contrapositive align with each other. Okay. So every one of these statements is an if-then statement. Okay. And the reason we name them, over here as converse, inverse, and contrapositive, that converse, inverse, contrapositive are if this statement here was my initial conditional. Does that make sense? But we could say that maybe this phrase here was my original conditional, and then off of that one, create the other three. Now, the other three, this might be, if this is my conditional, then my converse is going to be this one. Okay. If this is my conditional here, then this one is going to be, that one there is going to be my inverse, and this one will be my contrapositive. Does that kind of make sense? Okay. When they give you an if-then statement, you have trouble thinking about, is this true? Okay. Or you rephrase something, you have trouble thinking about, is it true? Try to find converse or inverse or contrapositive. And maybe analyze that and interpret that a little bit better. Does that make sense? Like I said, I have a very, very difficult time with the phrases that have not in them. So I reword them, try to find the truth value of their contrapositive or their converse or whatever, and that helps me analyze the actual phrase they're asking about. Okay. Just some. Let's skip that one for now. Let's get to the math ones here. Let's say if an angle is acute, then its measure is less than 180. Let's write these. So the conditional said if an angle is acute, then its measure is less than 180. Is that true or false? So if I give you an acute angle, you're saying that it could potentially have a measurement that's bigger than 180? This has got to be true, right? Okay. I'm not defining what an acute angle is here. I'm just providing a characteristic. If I hand you an acute angle, you automatically know that measurement is less than 180. Okay? you could better classify something else. Okay? But that's kind of the thing where we're reading into something that we don't want to read into. We just want to take this phrase as what it says and interpret that. And that's what a lot of people try to do. We want to try to avoid doing that. So if I take that phrase and come up with its converse, remember, converse is going to take the hypothesis, which this is the hypothesis, and it's going to put it at the end, right? It's going to put it after the word then, and it's going to take the conclusion, that's the conclusion, and it's going to put it after the word if. So I'm going to say if its measure is less than 180, then the angle is acute. Now, if it's less than 180, is it acute? Well, it could be acute, right? It could also be 90, so that's less than 180. We know we classify 90 as different than acute, right? It could be 100, and we know we classify that different than acute. Okay? So that is a false statement. Right? When you rewrite these things, grammatically speaking, like direct objects and all that kind of stuff, I'm not really going to like grade your grammar. But a lot of people like to write like if an angle is less than 180, then it is acute. So they take the angle part here, they put it over here. You know what you're talking about with the subject at the beginning. If you want to do that, that's fine. Doesn't really matter to me. Okay? So now I'm going to create the inverse. And I automatically know, before I do anything, I already know the truth value of the inverse. Because it's a fact. It's a geometric fact. The inverse is going to be what? What's its truth value? It's going to be false, right? The inverse is always the same truth value of the converse. Okay? So when I write the inverse, which is just taking this original phrase here, and putting the word not in front of it. If an angle is not acute, then its measure is not less than 180. Not less means what? Mathematically, not less than something would be greater than or equal to. Does that make sense? Okay. So I could rephrase it. If an angle is not acute, then it is greater than or equal to 180. If it's not acute, then it's greater than or equal to 180. That makes sense. If it's not acute, greater than or equal to 180, do we have a 90-degree angle in there? Yeah, there's a 90 degree would be a counterexample. Okay. Because it's saying greater than or equal to 180, you've got basically 90 up to 180 there, that fall into that category as counterexamples. So that is false. I think that's a hard question to answer, right? I think that's a very difficult question to determine whether that's true or false. So here's what happens. If in MathXL, they tell me that this is my conditional statement, I'm going to actually try to find its contrapositive. So if I can find its contrapositive and answer the contrapositive correctly, then I know how to answer that one correctly. Does that make sense? Okay. And that's really why we learn these phrases and then these different ways of rewriting them, is so that we can tell whether one is true or false when we have difficulty of interpreting it. So now the contrapositive, okay, is taking the first conditional statement, flip-flopping them, and then negating both of them. So I'm going to say if an angle is not less than 180, then it is not acute. And we know because the conditional was true, that has to be true. Okay? But if an angle is not less than 180, if it's not less than 180, then it's got to be greater than or equal to 180, right? So then it's like 181, 182, 183. Angles we haven't really talked about yet, but they exist. Then it's not acute. Well, is 181 acute? That's true thing, right? Okay. 182 is not acute. 183 is not acute. Okay. And that's what this is saying. This is categorizing those angles of 181, 182, 183. And we're saying if 182, then if my angle is 182, then it's not an equal. That's true. If my angle is 183, then it's not an equal. That's true. Going through them, all those infinite 181s, 182s, 183s, and making the argument then they are not acute. Does that make sense to everyone? Okay. Very important to remember that the conditional and contrapositive are logically equivalent. The inverse and the converse are logically equivalent. Let's do another one. Let's talk about get rid of this. We'll just talk about the truth values. All right, so I have the conditional statement. If two angles are adjacent, then they share a vertex. Hopefully you guys argue that is true because that's part of the definition for adjacent angles, right? Okay. The converse says if they share a vertex, then two angles are adjacent. Hopefully you realize that that is false because here's a counterexample. Those two angles right there share a vertex. They share that vertex in the middle, right? Okay. Let's look at talking about that blue angle and that green angle. They share a vertex, but are they adjacent? No. Okay. Call those vertical angles. Okay. So this is false. All right. Here it says if two angles are not adjacent, then they do not share a vertex. Well, again with the same picture, it's that angle there and that angle there. Do they satisfy that phrase right there? Are they not adjacent? Yeah. But do they share a vertex? Yes. This is saying that these two angles, because they're not adjacent, they should not share that vertex. But they do. We know that should be false. Again, if that phrase was hard to answer, if that inverse statement was hard to answer, look back at the converse. Maybe that was a little bit easier to answer, right? If converse was easier to answer, it's true or false, I now know the inverse is false automatically. Okay? And now once I know it's false and I struggle with that, now it gives me an idea or a way, and maybe I can justify that in my mind and draw some pictures and then maybe better analyze and understand that statement. Here it says that they do not share a vertex, then two angles are not adjacent. Maybe I struggle with answering that as true or false. I use the logically equivalent idea, conditionals and contrapositives, or is logically equivalent. Conditional is true, contrapositive is true. So they do not share a vertex, so maybe they have to be angles like that. They don't share a vertex, right? Can they be adjacent? No. And that's what it's saying. If they don't share a vertex, then they cannot be adjacent. And that's a true statement. Okay. Everything we come across in this course is going to be written as an if-then statement. And what I want you guys to understand, and this is an if-then statement that we've already seen in this course. People like to flip it around. People like to negate things and say that they gain the same information, always gain true statements from it. This is showing you, just because you flip the statement around, you do not get a true statement or true result. Does that make sense? Okay. So just because they're adjacent, and that means they share a vertex, does not mean that when two angles share a vertex, they have to be adjacent. All right? That makes sense? Okay. We want to make sure that we do not do that throughout all of mathematics. Just flipping something around is not a good idea. And a lot of times, when they give you a theorem, they give you a postulate, they write it as an if-then statement. They are telling you that's the only way you can read. You can't flip it around and get the same results. Does that make sense? Okay. But tomorrow, how they will write it, they want you to be able to flip it around and get the same results. Math Excel homework, 2.2. Finish that up, and you guys can go to lunch.